Picture the vast, silent expanse of space, a universe so immense it defies comprehension. Stars flicker like distant candles, galaxies whirl in endless spirals, and the laws of physics hold it all together. Or do they? What if hidden in the depths of the cosmos there are anomalies so bizarre they shatter everything we thought we knew? Imagine a force so strange, scientists call it the axis of evil, a cosmic mystery that doesn't just bend the rules of physics, it obliterates them. This isn't science fiction, it's real and it's out there, lurking in the fabric of reality itself. Think about the foundation of modern science, the laws that govern motion, gravity, even time. They're supposed to be unbreakable, universal. But what if they're not? The axis of evil is one of those terrifying, awe-inspiring wrinkles in the universe that makes even the brightest minds question everything. It's a pattern in the cosmic microwave background, the afterglow of the Big Bang that shouldn't exist. Some say it's a flaw in our measurements. Others whisper it's evidence of something far more unsettling, that our universe isn't what it seems. Could this be a glimpse into a deeper layer of reality, or is it a sign that the laws of physics are different in other parts of the cosmos? This is where the adventure begins. Today, we're diving into one of the most baffling enigmas of modern astrophysics, anomalies so strange they've been dubbed the axis of evil. These cosmic oddities don't just challenge our understanding, they threaten to rewrite it entirely. From regions of space where time might flow backward to mysterious voids that defy explanation, we'll explore the edges of known science and peer into the chaos beyond. By the end of this journey, you'll see the universe in a whole new light, one where the impossible might just be waiting to be discovered. So, are you ready to step into the unknown? Let's uncover the secrets that the cosmos has been hiding. The cosmic microwave background is like a snapshot of the universe taken just 380,000 years after the Big Bang, a faint glow of radiation that fills every corner of space. Scientists call it the oldest light in existence, a relic from when the cosmos was nothing more than a dense, searing plasma. Studying this afterglow is like holding up a magnifying glass to the universe's infancy, revealing clues about how everything began. But hidden in that ancient light is something deeply unsettling: patterns that defy explanation, alignments that shouldn't be possible. When researchers first mapped the cosmic microwave background in detail, they expected randomness, tiny fluctuations left over from the chaotic birth of the universe. Instead, they found eerie symmetries, strange alignments of hot and cold spots stretching across the sky like some cosmic fingerprint. The most baffling of these, a bizarre axis where these anomalies seem to line up in a way that contradicts the very foundation of modern cosmology. Scientists cheekily named it the axis of evil, not because it's malevolent, but because it undermines everything we thought we knew about the universe's structure. According to the standard model, the cosmos should be uniform in all directions, with no preferred axis, no hidden directionality. Yet the data tells a different story. Imagine rolling a dice 1,000,000 times and always getting the same number. That's how improbable this alignment is. Some argue it's just a fluke, a statistical anomaly in the data. Others think it might hint at something far stranger, an imprint from before the Big Bang, evidence of parallel universes brushing against ours, or even a sign that our universe is just one bubble in an infinite multiverse. The implications are staggering. If the axis of evil is real, it could mean the universe isn't as random as we believe. There might be a preferred direction to space itself, a cosmic north that challenges Einstein's assumption that no point in the universe is special. Or worse, what if our entire understanding of the Big Bang is incomplete? Could this anomaly be evidence of forces we haven't discovered yet, lurking in the shadows of physics? The more we study it, the more questions arise, leaving scientists torn between excitement and unease. This isn't just some abstract puzzle, it's a direct challenge to the laws that shape reality. And if history has taught us anything, it's that when the universe throws us a curveball, we're usually on the verge of rewriting the textbooks. So the next time you look up at the night sky, remember, there's more out there than meets the eye, and the biggest mysteries might be written in the oldest light of all. At the heart of this cosmic mystery lies a peculiar pattern so unsettling that it earned the dramatic nickname, the axis of evil. Picture the universe like a freshly baked loaf of bread. Scientists expected the cosmic microwave background to show random pockets of heat, like irregular air bubbles scattered throughout the dough. Instead, when they examined the data, they found something more like deliberate knife cuts long, unexplained alignments where hot and cold spots in the early universe's radiation mysteriously line up along a specific plane. This discovery throws a wrench into one of cosmology's most sacred principles, the cosmological principle, which states the universe should look roughly the same in every direction, no special places, no preferred axes. Like stirring cream into coffee, the massive energies of the Big Bang should have mixed everything into uniform randomness. Yet the axis of evil suggests the universe might have a hidden structure, almost as if space itself has a grain like wood running in one preferred direction. Think of it like spinning a globe. If Earth were perfectly isotropic, every latitude line would feel identical, no equator, no poles. But our planet has clear orientations where weather patterns and ocean currents organize themselves along specific lines. The axis of evil implies the universe might have its own invisible equator, a fundamental directionality that shouldn't exist if our current models are correct. Some researchers compare it to walking into a supposedly random forest and finding all the trees leaning at the exact same angle, the strangest part. This alignment seems to point suspiciously close to our solar system's plane. That's like discovering all the trees in the forest are leaning toward your house, an eerie coincidence that makes some scientists wonder if there's an observational bias at play. Could our instruments be picking up distortions from our own galactic neighborhood? Or does this alignment genuinely stretch across the cosmos, hinting that we're seeing a real universe-wide anomaly? There are theories, of course, some wilder than others. One suggests this could be evidence of a pre-Big Bang universe leaving ghostly imprints on our own. Another proposes that our universe collided with another bubble universe long ago, warping space-time like a fingerprint pressed into clay. Then there's the radical idea that dark energy, the mysterious force accelerating cosmic expansion, might not be uniform, but instead flows in currents that twist the fabric of reality itself. What makes the axis of evil so compelling is how it refuses to disappear. As telescopes get more advanced and data sets grow larger, the anomaly stubbornly persists, not getting stronger but never quite fading into statistical noise. It's the kind of puzzle that keeps cosmologists awake at night, torn between the thrill of potential discovery and the unease that their most basic assumptions might be wrong. After all, in science, the most exciting phrase isn't eureka, but that's funny. And right now, the universe is telling one of the oddest jokes we've ever heard. Every time we peel back a layer of cosmic mystery, we find new questions waiting underneath. The axis of evil isn't just a scientific curiosity. It's a reminder that the universe still holds cards it hasn't shown us yet. Whether it's a measurement error, a cosmic illusion, or proof of something fundamentally new, one thing's certain: our map of reality still has edges, and beyond them lies territory no one has ever explored. At the core of modern cosmology lies a rule so fundamental that calling it into question would be like arguing the Earth isn't round: the cosmological principle. This idea, bedrock to everything from Einstein's equations to our models of galactic evolution, states a simple but profound truth. On the largest scales, the universe has no favorite place, no special direction. It's homogeneous and isotropic, meaning matter and energy are spread evenly, with no cosmic up or down. That's why the axis of evil isn't just puzzling, it's revolutionary. If this anomaly is real, it doesn't just tweak our understanding of the universe, it bulldozes one of its foundational pillars. Imagine walking into a vast, endless desert where every dune, every grain of sand is perfectly identical in every direction. No landmarks, no slopes, just pure, featureless symmetry. That's how cosmologists have always pictured the universe, but the axis of evil suggests something far stranger. That hidden in this cosmic desert, there's an invisible path, a subtle groove running through reality itself. This isn't just about a few odd data points, it's about whether we've fundamentally misunderstood the shape of existence. The implications ripple outward like shockwaves. If space itself has a grain, a preferred orientation, then Einstein's assumption that the laws of physics are the same everywhere starts to crack. Could gravity behave differently along this axis? Might light bend in unexpected ways, even more unsettling? Could this explain other cosmic mysteries like dark energy's uneven distribution or why certain quasars seem to align across billions of light years? Some theorists speculate this might hint at something beyond our universe, like a gravitational tug from a neighboring dimension or relics from a previous cosmic cycle imprinted on spacetime. Skeptics argue it's all a mirage, an artifact of incomplete data or hidden measurement biases. After all, the cosmic microwave background is fiendishly hard to map, and our solar system's motion through space might be smearing the signal like fingerprints on a telescope lens. But every time scientists recalibrate their instruments or analyze new datasets, the anomaly lingers like a shadow that won't fade. What makes this debate so electric is what's at stake. Either we're seeing the first cracks in a theory that's held firm for a century, or we're witnessing the birth pangs of a new physics altogether. History shows us that when nature throws a paradox this glaring at us, like Mercury's wobbly orbit before relativity, or the ultraviolet catastrophe before quantum mechanics, it's usually a sign we're on the brink of something monumental. The axis of evil might just be the universe's way of whispering, "Look closer, there's more here than you've been taught." And if that's true, the textbooks of tomorrow could read very differently indeed. Whenever we're faced with a cosmic mystery as baffling as the axis of evil, the first question scientists ask isn't what new physics explains this, but rather, could our instruments be playing tricks on us? History is littered with discoveries that turned out to be measurement errors, like the infamous Martian canals that early astronomers swore they saw through their telescopes, only to realize later it was an optical illusion caused by atmospheric distortion. Even in modern cosmology, we've had false alarms. Take the BICEP 2 experiment in 2014, where researchers initially detected what they thought were gravitational waves from the Big Bang, only to discover the signal was actually cosmic dust. So is the axis of evil just another case of faulty data? On the surface, it's an easy explanation to reach for. Mapping the cosmic microwave background is like trying to photograph a faint candle flame from miles away while standing in a sandstorm. Our own Milky Way's gas, dust, and magnetic fields can distort the readings. Even the motion of our solar system barreling through space at over 800,000 kilometers per hour could theoretically imprint false patterns on the data, like streaks on a windshield during a rainstorm. But here's where things get interesting. Over the past 2 decades, multiple independent teams using completely different instruments, from the Planck satellite to ground-based telescopes in Antarctica and Chile, have all detected the same eerie alignment. It's as if 5 chefs using separate kitchens and recipes all baked cakes that inexplicably tilted to the northeast. The odds that all these experiments made the same exact mistake grow slimmer with each new dataset. Scientists have run exhaustive tests to rule out instrumental artifacts. They've modeled how galactic dust scatters light, calculated the precise Doppler shifts caused by Earth's motion, and even simulated how imperfections in telescope lenses might distort results. Yet after all that cleanup, the axis of evil remains, like a stubborn stain that won't scrub out. Some researchers have proposed even more exotic instrumental explanations like subtle quantum noise in the detectors themselves, but these ideas stretch plausibility further than the anomaly they're trying to explain. There's another telling clue. The axis of evil isn't just some minor statistical blip. It manifests at the largest scales of the universe across patches of sky billions of light-years wide. For an instrumental error to create such a coherent pattern across entirely separate observations would require a conspiracy of coincidences that defies probability. As one cosmologist put it, it'd be like every stoplight in New York City malfunctioning to always show green in one particular direction possible, but astronomically unlikely. That's not to say the case is closed. Science thrives on skepticism, and some researchers continue to hunt for overlooked systematic errors. But with each passing year, as instruments grow more precise and the signal persists, the burden of proof shifts. Maybe the universe isn't broken, maybe our understanding of it is. And that's when things get truly exciting, because nothing propels science forward like a good old-fashioned anomaly that refuses to be explained away. If cosmic inflation is the universe's opening act, a burst of exponential expansion that smoothed everything into uniformity, then why does the axis of evil look like a deliberate scribble across that perfect canvas? One compelling theory suggests that inflation itself might hold the key to this mystery, not because it worked flawlessly, but because it didn't. Imagine blowing up a balloon with tiny imperfections in its rubber. Stretching it to cosmic proportions could amplify those flaws into visible wrinkles. That's the essence of this idea. What if inflation wasn't perfectly symmetrical? What if it wobbled, stretched unevenly, or even collided with other inflating regions, leaving behind scars we now see as the axis of evil? Inflation theory was originally proposed to explain why the universe looks so smooth on large scales, but physicists have long known it doesn't require absolute perfection. Tiny quantum fluctuations during that hyper-expansion are what seeded galaxies and voids, so why couldn't larger asymmetries have formed too? Some models propose that inflation's energy field might have had lumps, like unevenly heated stovetop burners, causing space to stretch faster in some directions than others. Others speculate that our universe's inflation might have been interrupted, bumped by another inflating bubble universe, leaving behind a directional warp in space-time. The wildest version of this idea, that the axis of evil isn't just an artifact of wonky inflation, it's a message. If multiple bubble universes exist in a greater multiverse, their collisions could leave detectable imprints on the cosmic microwave background, like fingerprints on glass. The alignment we see might be the bruise from where our universe once brushed against another, a cosmic handshake frozen in ancient light. It's a tantalizing thought that we're not just mapping our own origins, but peering into a larger, hidden architecture of reality. Of course, not everyone's convinced. Critics point out that inflation is already a flexible theory. It can explain almost any observation by tweaking its parameters, which makes it hard to falsify. Calling on inflation to explain the axis of evil risks turning it into a theory of everything and nothing, a catch-all that loses predictive power. There's also the problem of scale. Inflation's quantum fluctuations are supposed to be random and minuscule, not organized into continent-sized patterns across the sky. For this explanation to hold, we'd need a new flavor of inflation, one that allows for large-scale anomalies without unraveling the theory's other successes. Perhaps the most intriguing twist is that even if inflation did cause the axis of evil, it doesn't actually solve the mystery, it just kicks it upstairs. Instead of asking why the cosmic microwave background looks strange, we'd be asking why inflation itself broke its own rules. Was it a one-off glitch or evidence of deeper physics governing the multiverse? The closer we look, the more the axis of evil feels like a breadcrumb trail, one that might lead us not just to the edge of our knowledge, but to the doorstep of realities beyond. Every explanation seems to open new questions, and that's the hallmark of a truly groundbreaking puzzle. Whether it's a flaw in our measurements, a quirk of inflation, or a window into the multiverse, the axis of evil refuses to let cosmology rest easy. And that's exactly how science moves forward, not by polishing old ideas until they shine, but by stumbling over the cracks that force us to rebuild them entirely. Just when you thought the axis of evil was the universe's strangest rebellion against physics, along comes another cosmic troublemaker, dark flow. Picture this: hundreds of massive galaxy clusters, each weighing as much as 1,000 Milky Ways, all drifting in the same direction like leaves caught in a hidden river. They shouldn't be moving this way. According to our best models, the universe's expansion should scatter galaxies evenly in all directions, like raisins in rising bread dough. But something out there, something we can't see, is pulling them off course with unimaginable force. This isn't just a gentle nudge. Dark flow sends clusters hurtling at speeds exceeding 3 million kilometers per hour toward a mysterious point in the distant cosmos beyond the observable universe. The most chilling part: this motion aligns eerily close to the same plane as the axis of evil, as if both anomalies are pointing toward the same cosmic north. That's too coincidental to ignore. Could they be two symptoms of the same underlying phenomenon, like ripples from a single, unseen stone thrown into the fabric of reality? Scientists first spotted dark flow in 2008 while studying the cosmic microwave background's subtle distortions. As galaxy clusters move, their hot gas scatters photons from the early universe, leaving faint streaks in the radiation like wake patterns behind speeding boats. When researchers mapped these streaks, they didn't cancel out randomly as expected. Instead, they revealed a coordinated march toward the constellations Centaurus and Hydra. The pull is so strong that even dark matter's gravity can't explain it. Whatever's causing this has to be something beyond our current physics, perhaps matter from a neighboring universe tugging on ours, or relics from a previous cosmic cycle exerting leftover influence. Here's where it gets speculative but thrilling. Some theorists propose that dark flow might be evidence of a super-universe beyond our cosmic horizon. Imagine standing in a valley surrounded by mountains you can't see. Their gravitational pull could still affect the rivers flowing nearby. Similarly, if a vastly larger structure exists outside our observable bubble, like a neighboring universe or an uneven distribution of spacetime itself, it might be dragging everything toward it. Others suggest this could be the fingerprint of quantum entanglement operating at cosmic scales, linking our universe to another through invisible threads. The stakes couldn't be higher. If dark flow and the axis of evil are connected, we're not just looking at isolated oddities, we're glimpsing the outlines of a far grander architecture. It's like finding two pieces of a jigsaw puzzle that don't fit the picture you've been assembling, hinting that the real image is something entirely different. Every time we think we've mapped the universe's boundaries, anomalies like these whisper, "Look further." The cosmos isn't just bigger than we imagined. It's stranger, wilder, and more defiant of our rules than we ever dared to dream. What if our universe isn't alone? The axis of evil's eerie alignment might be more than just a cosmic coincidence. It could be a fingerprint left by another universe brushing against ours. This isn't science fiction. The multiverse hypothesis, once relegated to the fringes of theoretical physics, is now a serious topic of debate among cosmologists. And the strange patterns in the cosmic microwave background might be our first tangible clue that we're not the only bubble in the cosmic froth. Think of the multiverse like a vast ocean, with each universe a separate bubble rising from its depths. Most bubbles float independently, never touching, but sometimes they might graze each other, leaving faint imprints where they meet. If another universe drifted close to ours during inflation, that explosive moment of cosmic expansion, its gravity could have warped our spacetime, creating a directional bias we now detect as the axis of evil. It's like finding a dent in a car door after a parking lot scrape, except here, the dent is a billion light-year-wide anomaly in the fabric of reality. The math behind this idea isn't as far-fetched as it sounds. Inflationary theory already suggests that universes could sprout endlessly like branches on a tree. Some variants, like brain cosmology, propose that our universe exists on a higher dimensional membrane that might occasionally collide with others. These collisions wouldn't be cataclysmic, more like ghosts passing through walls, leaving subtle gravitational echoes. The axis of evil could be one such echo, a relic of a long-ago encounter with a universe whose physical laws might be utterly alien to ours. Critics argue this is speculation dressed up as science. After all, we can't observe beyond our cosmic horizon. But supporters counter that the multiverse isn't just a wild guess. It's a natural extension of quantum mechanics and inflation. And if the axis of evil really is a sign of a neighboring universe, it would solve two puzzles at once: the anomaly's existence and why it aligns so suspiciously with dark flow. Both could be pointing toward the same external gravitational pull, like compass needles drawn to a hidden magnet. The implications are staggering. If true, we're not just mapping our universe, we're glimpsing an infinite archipelago of realities, each with its own laws of physics. Some might harbor exotic matter we can't imagine. Others could be lifeless voids or teeming with civilizations. And if we're seeing the gravitational shadow of one, how many more lie beyond? The axis of evil might be the first thread in a tapestry of universes, one we're only just beginning to unravel. Of course, extraordinary claims require extraordinary evidence. The multiverse remains untestable by traditional means, and many scientists prefer explanations rooted in our own universe's physics. But that's the beauty of anomalies like this. They force us to question, to imagine, to push the boundaries of what's possible. Whether the axis of evil is a sign of the multiverse or just a quirk of quantum fluctuations, one thing's certain: the cosmos is far stranger than we ever dreamed. And that's what makes the search so thrilling. For centuries, gravity and quantum mechanics have existed in separate realms, one governing the cosmic dance of planets and galaxies, the other ruling the chaotic subatomic world. But what if the axis of evil is a bridge between these two domains? Quantum gravity, the long-sought theory to unify these fundamentally different forces, might hold clues to this cosmic riddle. At the universe's birth, when everything was compressed into a space smaller than an atom, quantum effects could have imprinted irregularities on spacetime itself. Like wrinkles frozen in a sheet of ice, these primordial quantum fluctuations might have stretched into the vast patterns we now call the axis of evil. Take loop quantum gravity, one of the leading candidates for a theory of quantum gravity. It suggests spacetime isn't smooth and continuous but woven from tiny, indivisible loops, a fabric with a granular texture. At the universe's inception, these loops could have vibrated in specific ways, creating asymmetries that inflation then blew up to cosmic proportions. Picture throwing a handful of confetti into a hurricane. The initial arrangement of those tiny pieces could determine the storm's final pattern. Similarly, quantum loops might have dictated how spacetime stretched, leaving behind the eerie alignments we observe today. String theory offers another tantalizing possibility. If fundamental particles are actually vibrating strings in higher dimensional space, their earliest harmonies might have resonated across the infant universe like echoes in a cathedral. Certain string configurations could produce preferred directions in spacetime, subtle biases that eventually manifested as the axis of evil. Some versions of the theory even suggest our universe is a four-dimensional brain floating in a higher dimensional bulk. Collisions or interactions with other brains might have tilted our cosmic playing field, leaving a directional fingerprint imprinted in the cosmic microwave background. Then there's the wild card: quantum entanglement operating at cosmic scales. Normally, entanglement links particles across tiny distances, but if it somehow influenced the early universe's structure, it could have created large-scale correlations. Regions of space mysteriously synced up despite being too far apart to interact. The axis of evil might be a ghostly remnant of this quantum synchronicity, a snapshot of the universe's earliest interconnectedness before decoherence scrambled the signal. Not everyone's convinced, of course. Critics argue that quantum gravity's mathematics remains too fuzzy to make testable predictions about something as specific as the axis of evil. Others counter that invoking untested theories to explain anomalies risks creating, just so, stories' explanations flexible enough to fit any observation without offering real proof. But supporters point out that every major breakthrough in physics began as a speculative leap. Einstein's relativity emerged from thought experiments about light beams and moving trains, not hard data. Maybe the axis of evil is our generation's equivalent, a cosmic oddity nudging us toward the next paradigm shift. What makes this quest so electrifying is the possibility that we're not just solving a puzzle about the universe's structure. We might be catching our first glimpse of quantum gravity in action. If the axis of evil truly stems from quantum effects written across the sky, it's like discovering the universe's baby photos, complete with the microscopic quirks of its birth. Whether loop quantum gravity, string theory, or something entirely unexpected holds the key. One thing's certain: the answer won't just rewrite cosmology textbooks, it could redefine reality itself. Among the most exotic relics predicted by theoretical physics are cosmic strings, flaws in the fabric of spacetime itself, thinner than a proton but stretching across the entire universe. Picture the universe cooling after the Big Bang like molten metal solidifying, and cosmic strings as the cracks that form as it hardens. These aren't made of matter or energy, but pure spacetime geometry, infinitely dense, one-dimensional scars left over from the universe's earliest moments. Their gravitational pull would be so immense, a single string just 6 miles long could outweigh the entire Earth. And if they exist, they might be the architects behind the axis of evil's bizarre alignment. The math behind cosmic strings emerges naturally from certain grand unified theories. When the fundamental forces of nature first split apart, like ice crystallizing into different patterns, they could have trapped imperfections in spacetime structure. These defects wouldn't behave like ordinary objects. A cosmic string would be nearly invisible, yet anything passing near it would experience extreme gravitational lensing, as if space itself were a funhouse mirror. Galaxies on either side of a string might appear duplicated in the sky, while light skimming its edge could wrap around it like thread on a spool. Most startlingly, cosmic strings could vibrate at relativistic speeds, creating ripples in spacetime so powerful they might briefly outshine entire galaxies in gravitational waves. Now imagine such a string slicing through the early universe during inflation. As spacetime expanded exponentially, the string's gravitational field would have stretched with it, warping the cosmic microwave background in its wake. The axis of evil's alignments could be the fossilized imprint of this distortion, a vast, straight crease pressed into the universe's oldest light. Some simulations suggest that if a cosmic string were oriented just right, it could create precisely the kind of planar asymmetry we observe, like a scratch across a vinyl record that skews the music in one direction. But here's the twist: cosmic strings wouldn't just bend light, they'd fracture time. According to general relativity, moving near a string at near light speeds could create closed time-like curves, effectively allowing time travel to the past. This raises a dizzying possibility. Could the axis of evil be evidence of a spacetime defect so extreme it briefly twisted causality itself during the universe's infancy? The idea sounds like science fiction, but the equations allow it. If true, the cosmic microwave background might carry echoes of events that haven't happened yet, scrambled into patterns we're only beginning to decipher. Despite their theoretical elegance, cosmic strings remain controversial. No direct evidence for them exists yet, though astronomers have searched for their signatures in everything from galaxy distributions to gravitational wave data. Some argue that even if strings formed after the Big Bang, inflation would have diluted them beyond detectability, leaving only faint traces like the axis of evil. Others propose hybrid theories. Perhaps strings interacted with dark energy or collided with other defects, amplifying their imprint. What makes cosmic strings so compelling as an explanation isn't just their ability to solve the axis of evil puzzle, but their sheer audacity. They remind us that the universe's birth wasn't a smooth, polished event. It was a messy, violent process that might have left scars we can still see today. Whether these space-time cracks are real or not, their possibility stretches our imagination to the limit, forcing us to confront a cosmos far stranger than we ever expected. And if they're out there, lurking in the darkness between galaxies, they might be the closest thing we've found to the universe's original blueprints, written not in ink, but in the twisted geometry of space-time itself. What if the axis of evil isn't a flaw in the universe, but a flaw in the simulation of the universe? This isn't just the plot of a sci-fi movie. Some scientists and philosophers seriously entertain the idea that our reality might be an advanced digital construct, and cosmic anomalies like the axis of evil could be glitches in the code. Think of it like finding a pixelated texture in a video game, a tiny slip in the rendering that hints at the artificial framework underneath. If the universe is a simulation, then the axis of evil might be the equivalent of a software bug, a telltale sign that the program running our existence isn't perfect. The simulation argument gained traction when philosopher Nick Bostrom proposed that an advanced civilization with enough computing power might one day create ancestor simulations, detailed virtual worlds indistinguishable from reality. If such simulations outnumber the one base reality, the odds suggest we're more likely to be inside one than outside. Physicists have since toyed with ways to test this idea. Some suggest looking for computational shortcuts, places where the programmers might have cut corners to save processing power. Others hunt for anomalies that defy natural laws, like the axis of evil's inexplicable alignment. After all, in a simulated universe, even the laws of physics could be arbitrary lines of code, and glitches would reveal where those lines fray. Critics, of course, dismiss this as unfalsifiable speculation. Science requires testable hypotheses, and proving we're in a simulation is like a character in a novel trying to find the author's pen. But supporters counter that certain signatures, like the axis of evil's unnatural symmetry, could act as empirical red flags. In a simulated cosmos, the microwave background might display artifacts of numerical approximations or lattice boundaries in the underlying code. The alignment could be a relic of the simulation's coordinate system, a cosmic axis around which the virtual universe renders. Even dark flow's mysterious pull might fit this narrative. Imagine it as the gravitational shadow of another simulation running adjacent to ours, its code briefly leaking into our domain. Here's where it gets even stranger. If the universe is a simulation, the axis of evil might not be a mistake at all. It could be intentional, a breadcrumb left by the creators. Ancient programmers might have embedded clues in the cosmic microwave background, knowing their simulated descendants would one day decode them. Or perhaps the anomaly is a debugging tool, a way to monitor how the simulation handles contradictions in its own rules. Some theorists go further, suggesting that quantum mechanics' inherent uncertainty isn't a fundamental property of nature, but a feature of the simulation's limited processing power, like a computer approximating physics to save resources. Yet for all its intrigue, the simulation hypothesis remains a fringe idea in mainstream physics. The biggest hurdle: it doesn't actually explain why the axis of evil exists, it just relabels the mystery. Calling something a glitch doesn't clarify its mechanics any more than calling lightning Zeus's anger explained electricity. Worse, it risks becoming a modern-day God of the gaps argument, inserting simulation theory wherever science hits a wall. As one cosmologist put it, invoking programmers to explain cosmic anomalies is like invoking fairies to explain rustling leaves. It might feel satisfying, but it doesn't advance understanding. But maybe that's missing the point. The value of the simulation argument isn't in proving we're living in a matrix, it's in questioning the very nature of reality. If the axis of evil forces us to consider whether the universe might be artificial, it also reminds us how little we truly grasp about the fabric of existence. Whether we're in a simulation or not, the cosmos is clearly more complex than our models can capture. And that's the real takeaway. The universe, real or rendered, still has secrets we've only begun to uncover. So the next time you stare at the night sky, wondering about the axis of evil's strange alignments, ask yourself this: does it matter if the mystery stems from physics or firmware? Either way, we're left with the same exhilarating challenge, deciphering the rules of a reality far stranger than we ever imagined. Science has a long history of staring into the cosmos only to have the cosmos stare back with defiance. The axis of evil isn't the first anomaly to rattle our understanding of the universe, it's just the latest in a centuries-long parade of cosmic curveballs that forced scientists back to the drawing board. Take dark matter, for example. Back in the 1930s, astronomer Fritz Zwicky noticed something bizarre about the Coma galaxy cluster. The galaxies were moving so fast that their visible mass couldn't possibly hold them together. It was as if the cluster had some invisible skeleton, a hidden scaffold of gravity with no light to betray its presence. His peers dismissed it at first, but decades later, Vera Rubin's observations of spinning galaxies confirmed it. 85% of the universe's matter was missing. The dark matter Zwicky proposed wasn't just real, it was the universe's dominant architecture lurking unseen in the shadows. Then came the shock of 1998, when two teams studying distant supernova made a discovery so jarring it won them a Nobel Prize. Instead of slowing down as expected from the Big Bang's momentum, the universe's expansion was speeding up, as if some invisible force were stretching space itself apart. Scientists called it dark energy, a placeholder name for whatever's causing this anti-gravitational push. Overnight, our cosmic narrative flipped. The universe wasn't just expanding, it was accelerating toward an uncertain fate, driven by a mystery that makes up 68% of reality's energy budget. Both dark matter and dark energy shared a common thread. They were gaps in our understanding so vast, they demanded entirely new physics to explain them. The axis of evil joins this hall of fame of cosmic rebellions, but with a twist. While dark matter and energy challenged what the universe is made of, this anomaly questions how it's structured on a fundamental level. Its alignments suggest the universe might have a preferred orientation, a cosmic north, that violates the sacred cosmological principle. That's not just adding new ingredients to the recipe, it's suggesting the kitchen itself might be crooked. History shows us a pattern. Every time we think we've mapped reality, the universe laughs. Newton's clockwork heavens gave way to Einstein's warped spacetime. The static, eternal cosmos yielded to the Big Bang's explosive birth. Even the steady expansion of space surprised us by accelerating. Each of these revolutions began with an anomaly that didn't fit: a wobble in Mercury's orbit, the redshift of galaxies, or the cosmic microwave background's faint glow. The axis of evil could be the next domino in this chain, a clue that our current model, for all its triumphs, is still incomplete. What's remarkable isn't just how often science gets appended, but how resistant we are to it. When Einstein introduced relativity, it took years for physicists to abandon Newtonian mechanics, even as evidence piled up. Dark matter faced decades of skepticism before becoming textbook knowledge. The lesson: science progresses not by gracefully accepting upheaval, but by clinging to old paradigms until anomalies leave no other choice. The axis of evil might be at that tipping point now, a stubborn discrepancy that refuses to vanish, whispering that our universe's story is far from fully told. So when you hear someone dismiss the axis of evil as a statistical fluke, remember, that's exactly what they said about the expanding universe, about black holes, about the quantum weirdness underlying reality. The most transformative discoveries often start as inconvenient truths, outliers that demand we rethink not just the answers but the questions themselves. Whether this anomaly fades into obscurity or reshapes cosmology, one thing's certain: the universe still holds surprises that'll make our current confusion look quaint. And that's what makes the search so exhilarating. To uncover the universe's deepest secrets, scientists needed more than ground-based telescopes. They needed instruments floating beyond Earth's distorting atmosphere, staring into the void with unprecedented precision. Enter NASA Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001. Its mission: to map the cosmic microwave background with such clarity, it would reveal the universe's infant portrait in exquisite detail. For 9 years, WMAP orbited a point a million miles from Earth, shielded from solar interference, meticulously recording temperature fluctuations in the afterglow of the Big Bang. The data it sent back was nothing short of revolutionary. WMAP all-sky maps showed the cosmos wasn't just speckled with random hot and cold spots. It had odd, large-scale asymmetries, subtle but unmistakable. Most startling was the discovery of a plane bisecting the sky where these anomalies seemed to align, like invisible threads pulling the universe's fabric taut. Scientists jokingly dubbed it the axis of evil, but the name stuck because the implications were anything but funny. WMAP findings were so bizarre, the scientific community demanded verification. Enter the Planck satellite, a European Space Agency mission with even sharper eyes. Launched in 2009, Planck's instruments were 10 times more sensitive, capable of detecting temperature variations as tiny as 1/1,000,000th of a degree. For over 4 years, it scanned the sky, cross-checking WMAP results with colder, harder data. When Planck released its first full sky map in 2013, the scientific world held its breath. There it was again, the same eerie alignments, the same axis of evil, now etched into the cosmos with even greater clarity. Planck didn't just confirm WMAP anomaly, it deepened the mystery. The alignments weren't artifacts, they were real. What makes these missions so extraordinary is their painstaking reliability. WMAP and Planck didn't just snap pictures, they accounted for every possible contaminant. Galactic dust mapped and subtracted, the Milky Way's magnetic field measured and corrected. Even the faint glow of electrons racing through galaxy clusters was filtered out. The data was scrubbed cleaner than a surgical instrument, yet the axis of evil remained, like a stubborn stain on reality's blueprint. Both missions used entirely different instruments, WMAP with its differential radiometers, Planck with its bolometers, yet arrived at the same unsettling conclusion. That's like two chefs using different ovens and recipes but pulling out identical, oddly misshapen loaves of bread. The odds of a systematic error causing this vanish into statistical impossibility. Planck's precision revealed another layer to the puzzle. The anomalies weren't just on one scale. They appeared across multiple angular sizes in the sky, like a fractal mystery repeating itself. Some theorists hoped higher resolution data would break the alignments into randomness, but Planck showed the opposite. The larger the scale, the more pronounced the asymmetry. It's as if the universe has a grain, like wood, and we're seeing the direction it was sanded. Even stranger, the axis roughly aligns with our solar system's plane, a coincidence so improbable it's either a cruel trick of perspective or a hint that we're seeing something fundamental about spacetime itself. The legacy of WMAP and Planck isn't just in the questions they answered, but the ones they forced us to ask. These missions were designed to confirm cosmology's standard model, not append it. Yet here we are, staring at data so robust it can't be ignored, yet so bizarre it can't be explained. Whether the axis of evil is a cosmic coordinate system we've yet to understand, a shadow from a neighboring universe, or evidence of physics beyond Einstein's reach, one thing's certain: the universe is still keeping its deepest secrets close. And that's what makes the hunt so thrilling. Not every physicist loses sleep over the axis of evil. In fact, some argue it's less a cosmic conspiracy and more a case of seeing shapes in the clouds, a classic example of apophenia, where the human brain finds patterns even in randomness. They point out that when you're dealing with something as vast and complex as the cosmic microwave background, statistical flukes are inevitable. It's like flipping a coin 1,000,000 times. You'd expect some improbable streaks of heads or tails purely by chance. The skeptics' rallying cry: extraordinary claims require extraordinary evidence. And in their view, the axis of evil hasn't cleared that bar yet. Take the argument of calibration bias. Our telescopes, no matter how advanced, are still human-made instruments peering through the fog of our own galaxy. Dust, magnetic fields, even the motion of our solar system could subtly distort measurements. Imagine trying to photograph a faint candle flame while standing in front of a bonfire. The Milky Way's glare might be warping the data in ways we haven't fully accounted for. Critics highlight that when researchers apply different statistical techniques or tweak their foreground subtraction methods, the axis of evil's significance sometimes weakens. It's a bit like adjusting the contrast on a photo. What looked like a face in the shadows might just be a trick of the light. Then there's the look elsewhere effect. With a sky full of fluctuations, the odds increase that some alignment will appear striking purely by random chance. If you search through enough data, you're bound to find something odd, like rolling dice, until you finally get snake eyes and declaring the dice loaded. Some statisticians argue the axis of evil is just that, a cosmic coincidence elevated to mythic status because it's weird, not because it's meaningful. After all, if you slice the cosmic microwave background along enough arbitrary planes, one of them is bound to seem suspiciously orderly. But the most damning critique comes from Occam's razor, the principle that the simplest explanation is usually the right one. Invoking parallel universes, cosmic strings, or simulation glitches to explain the axis of evil feels like using a flamethrower to light a candle. Why leap to exotic physics when mundane explanations, instrumental noise, overlooked systematics, or plain old statistical noise are still on the table? As one skeptic quipped, before you rewrite cosmology, maybe check your telescope for smudges. Yet even the staunchest critics admit the axis of evil won't vanish just because it's inconvenient. The fact that multiple independent missions, WMAP, Planck, and others keep detecting similar anomalies forces them to concede something is there. The debate isn't whether the data shows an odd alignment, it's whether that alignment matters. For every physicist calling it a measurement artifact, another whispers it might be the first crack in the foundation of modern cosmology. What's fascinating is how this divide mirrors historical scientific battles. When the cosmic microwave background was first discovered in 1965, some dismissed it as pigeon droppings on the antenna. When dark energy was detected decades later, many assumed it was an observational error. Science thrives on this tension between skepticism and revelation, between dismissing anomalies and chasing revolutions. The axis of evil sits squarely in that crossroads, a Rorschach test for how we confront the unknown. So who's right? The answer might lie in the next generation of experiments. Projects like the Simons Observatory and future space-based telescopes promise data so precise, they'll either dissolve the anomaly into noise or etch it permanently into the canon of cosmic mysteries. Until then, the axis of evil remains a tantalizing maybe, a reminder that in science the most dangerous thing isn't being wrong, it's being certain too soon. Deep in the direction of the constellations Centaurus and Hydra, something massive is pulling at our galaxy and thousands of others with the gravitational grip of 100 quadrillion suns. Astronomers call it the Great Attractor, a mysterious region of space where galaxies stream like rivers toward an unseen delta. What's bizarre isn't just its existence, but its location, roughly the same patch of sky where the axis of evil's alignments point. That's no coincidence. It's a cosmic clue that these two anomalies might be threads of the same unraveling mystery. The Great Attractor was discovered in the 1970s when astronomers noticed our Milky Way, along with countless other galaxies, racing toward it at over 2 million kilometers per hour. At first, they assumed it was just a dense cluster of galaxies, but when they looked closer, something didn't add up. The visible mass there was nowhere near enough to explain the gravitational pull. It's as if we're being dragged toward a ghost, an invisible leviathan lurking behind the curtain of the observable universe. Sound familiar? The same eerie, something's missing feeling haunts both the Great Attractor and the axis of evil. Now here's where it gets spine-tingling. The Great Attractor lies along what's called the zone of avoidance, a region of space obscured by the Milky Way's thick dust and stars. It's like trying to study a mountain peak through a blizzard. We know there's something there, but the details are frustratingly blurred. Could this hidden gravitational vortex be warping spacetime in ways that leave imprints on the cosmic microwave background? Some theorists suggest the axis of evil's alignments might be shadows cast by the Great Attractor's immense gravity, bending ancient light like a lens distorting a flashlight beam across a wall. But there's a twist. The Great Attractor itself might not be the true source of this pull. Recent observations reveal it's just one piece of an even larger puzzle, a supercluster of galaxies called Laniakea, meaning immense heaven in Hawaiian. This cosmic web stretches over 500 million light-years, with galaxies flowing like tributaries toward a gravitational nadir we still can't fully map. If the axis of evil aligns with this flow, it could mean we're seeing the universe's scaffolding not just a local anomaly, but a fundamental asymmetry in the distribution of matter and energy since the Big Bang. Critics argue that correlation isn't causation. The sky is vast, and lining up two oddities doesn't prove they're connected. But supporters counter with a striking observation. Both anomalies hint at the same underlying idea that the universe isn't as uniform as we thought. Whether it's the Great Attractor's gravitational tug or the axis of evil's microwave alignments, both suggest a cosmos with a hidden structure, a cosmic grain that challenges the very principle of isotropy. The most tantalizing theory that these phenomena are symptoms of something even grander, a relic from the universe's birth. If inflation, the rapid expansion after the Big Bang, wasn't perfectly symmetrical, it could have left behind wrinkles in spacetime that later condensed into gravitational anomalies and microwave asymmetries. Picture blowing up a balloon with a weak spot. As it expands, that flaw stretches into a visible scar. The Great Attractor and the axis of evil might be different faces of the same primordial imperfection. Or perhaps it's darker than that. Some models propose that dark energy, the force accelerating the universe's expansion, isn't evenly distributed. Instead, it might flow in rivers, pooling in some regions and leaving others empty. If these currents intersect near the Great Attractor, they could simultaneously warp galaxy motions and imprint the cosmic microwave background with strange alignments. It's a radical idea that dark energy isn't a static force but an active, dynamic player in shaping the cosmos. Whatever the truth, one thing's clear: the universe keeps handing us puzzles that refuse to fit neatly into our models. The Great Attractor and the axis of evil aren't just scientific curiosities, they're signposts pointing toward gaps in our understanding, whispering that the story we've told about the cosmos is still missing chapters. And that's the thrill of exploration, not just filling in the blanks, but realizing how many blanks we never knew were there. What if gravity itself is the problem? For centuries, we've assumed Newton and Einstein had the final word on how mass bends space and tugs on celestial bodies. But when faced with cosmic oddities like the axis of evil, some physicists wonder, could our understanding of gravity be incomplete? Enter modified Newtonian dynamics, a radical idea that suggests gravity behaves differently on cosmic scales than our equations predict. Instead of invoking dark matter or multiverses, Mund proposes a simpler fix: tweak the math and the mysteries might vanish. At its core, Mund challenges a fundamental assumption that gravity weakens with distance according to Newton's inverse square law. In the 1980s, physicist Mordechai Milgrom noticed something peculiar about galaxy rotations. Stars at the edges of spiral galaxies whirled too fast for the visible mass to hold them in orbit, just as Zwicky observed in galaxy clusters. But instead of blaming invisible dark matter, Milgrom suggested gravity might strengthen slightly at extremely low accelerations, the kind found in a galaxy's faint outskirts. Adjust the formula and suddenly, galaxies rotate exactly as observed without needing dark matter's phantom grip. It's like realizing your car's speedometer was mislabeled all along. The problem wasn't the engine but the gauge. Now apply that same logic to the axis of evil. If gravity doesn't play by the rules we've assumed, large-scale structures might align in ways that defy standard cosmology. Mund proponents argue that subtle changes in gravitational behavior could create preferred directions in space-time cosmic currents that nudge matter into eerie symmetries. Picture a river flowing downhill. Normally, water spreads evenly, but if the ground tilts imperceptibly, the whole current shifts. Similarly, a tweaked gravity might funnel the universe's expansion along unseen gradients, imprinting the cosmic microwave background with the axis of evil's strange alignments. But here's the catch. While Mund excels at explaining galaxy rotations, it stumbles over bigger puzzles. The bullet cluster, a cosmic collision where visible gas lags behind galaxies, shows gravitational lensing that matches dark matter's predictions, not Mund. The theory also struggles to account for the precise fluctuations in the cosmic microwave background without adding extra ingredients. Critics argue it's like fixing a leaky faucet only to flood the basement, solving one problem while creating others. Yet Mund isn't alone. Some theorists have hybridized it with dark matter, suggesting gravity might modify at certain scales while still allowing for unseen mass. Others propose relativistic versions like tensor vector scalar gravity, where spacetime itself has hidden properties that alter large-scale dynamics. These ideas remain controversial, but they share a thrilling premise: that the axis of evil might not need parallel universes or simulation glitches to explain it. Maybe we've just been calculating gravity wrong all along. The real test: predictions. A good theory doesn't just explain existing data, it forecasts new observations. Mund, for instance, predicts specific patterns in galaxy rotations that dark matter models don't. If future telescopes find these fingerprints, it could upend cosmology overnight. Similarly, if the axis of evil's alignments trace back to gravitational tweaks, upcoming missions like the European Space Agency's Euclid telescope might spot corroborating bends in spacetime. Until then, modified gravity remains a bold underdog, a reminder that sometimes the most elegant solutions hide in the margins of our textbooks. So the next time you hear about cosmic anomalies, ask yourself, are we missing matter or misreading the rules? The answer could rewrite not just the axis of evil's story, but the very laws that bind the universe. The next generation of space telescopes won't just gaze deeper into the cosmos, they'll hunt for answers to the axis of evil with instruments so precise they could spot a candle flicker on Pluto. Leading the charge is NASA's Nancy Grace Roman Space Telescope, set to launch in the mid-2020s. Unlike its predecessors, Roman won't just map the cosmic microwave background, it'll dissect it with a wide-field infrared camera capable of surveying the sky 50 times faster than Hubble. Scientists hope its panoramic view will reveal whether the anomaly is a local quirk or woven into the universe's fabric. Imagine having only a blurry Polaroid of a crime scene, then suddenly switching to ultra-high-definition video. That's the leap Roman promises, potentially exposing hidden gravitational distortions or large-scale structures that could explain the alignments. Meanwhile, the European Space Agency's Euclid mission is already on the case. Launched in 2023, this dark energy detective will chart the distribution of galaxies and dark matter across 10 billion light-years, searching for invisible forces that might be warping spacetime along the axis of evil's plane. Euclid's specialty, measuring cosmic shear, the subtle stretching of galaxy shapes by intervening mass. If dark matter or exotic energy flows preferentially along the anomaly's axis, Euclid's razor-sharp optics could catch it red-handed. Think of it as dusting for fingerprints on a cosmic scale, where every distorted galaxy is a clue pointing to the culprit behind the universe's odd tilt. But the real game-changer might be the proposed CMB-S4 project, a ground-based array of telescopes in Chile and Antarctica designed to scan the cosmic microwave background with unprecedented sensitivity. With over 500,000 detectors, it'll spot temperature variations 100 times fainter than those Planck detected. The goal? To isolate the axis of evil's signal from all possible contaminants, galactic dust, foreground emissions, even quantum noise in the detectors themselves. If the anomaly persists under this scrutiny, it'll silence skeptics who dismissed it as measurement noise. If it vanishes, cosmology can breathe a sigh of relief. Either way, CMB-S4 won't just observe the cosmos, it'll put it on trial. Then there's the audacious concept of a cosmic action detector, designed to hunt for hypothetical particles called actions that might flow along the axis of evil's plane. Some theorists suggest these ghostly particles, if they exist, could interact with primordial magnetic fields, leaving behind the alignments we see today. It's a long shot, but so was dark matter once. Future missions might also deploy gravitational wave detectors like LISA, a space-based observatory that could sense ripples from cosmic strings or early universe collisions that left directional scars. What unites these missions is a shared obsession: precision. The axis of evil isn't just a puzzle, it's a test of whether our understanding of the universe holds up under the most extreme scrutiny. Every new telescope is a gambit, a bet that somewhere in the flood of data, a pattern will emerge that either shatters our models or confirms them. And that's the thrill of the hunt, not just answering old questions, but discovering new ones we never thought to ask. The universe has kept its secrets for 13.8 billion years, but its walls are starting to crack. For centuries, science has operated under a quiet assumption that the universe is fundamentally random, a vast expanse where no direction is special and no corner holds privilege over another. This principle of isotropy isn't just academic, it's the bedrock of cosmology, woven into everything from the Big Bang's equations to our models of galaxy formation. Yet the axis of evil whispers an unsettling question. What if the cosmos isn't as indifferent as we thought? What if it has a grain, a tilt, a hidden structure that betrays something deeper at play? Consider the implications. If the universe truly has a preferred axis, an invisible spine around which its mysteries align, it would mean reality isn't just a chaotic accident. There's a fingerprint here, an architecture that suggests order beyond randomness. Some theorists liken it to walking into a forest where every tree leans slightly east. At first glance, it might seem like chance, but when you notice the same slant in every grove across every continent, you start wondering, is there a prevailing wind shaping everything? The axis of evil could be that wind, a force or framework we've yet to comprehend, bending the universe to its will. This isn't just about rearranging equations. It strikes at the heart of how we see our place in the cosmos. A random universe is democratic, unguided, indifferent, but a structured one that opens doors to possibilities both thrilling and unnerving. Perhaps the alignments are relics of a deeper physics, a shadow of higher dimensional geometry or quantum entanglement operating at scales we can't yet measure. Or maybe, as some philosophers speculate, they hint at something even more profound, that the universe isn't just ordered but purposive. Not in the religious sense, but in the way a river carves a canyon, obeying laws that give rise to patterns we're only beginning to decode. Of course, not everyone's ready to abandon the comfort of randomness. Critics argue that calling the axis of evil evidence of cosmic design is like seeing a face in the clouds, a trick of perception, not reality. They point out that nature is full of apparent patterns that dissolve under scrutiny. The spiral arms of galaxies, the branching of trees, even the distribution of prime numbers, all seem deliberate, yet emerge from simple, impersonal rules. Why should the cosmic microwave background be any different? But here's the counterpoint. Science's greatest leaps often come from questioning the very things we take for granted. Einstein upended Newton's absolute time. Quantum mechanics shattered determinism. Each time, the universe revealed itself to be stranger than we imagined. The axis of evil might be another such pivot point, urging us to consider that randomness isn't the default, it's the exception. Dig deeper and the questions grow richer. If the universe is structured, what does that mean for the multiverse theory? Could our cosmos be one of many in a foam of realities, each with its own axis, its own rules? Or is this alignment a cosmic fossil, evidence of a time before the Big Bang when the laws of physics were set in motion? The philosopher in you might even wonder, if the universe has a direction, does it have a directionality, not just in space but in purpose? We may never know for certain. But that's the beauty of the axis of evil. It's not just a puzzle to solve, it's a mirror held up to our assumptions. Every time we think we've mapped reality's edges, the cosmos reminds us the unknown isn't just beyond us. It's written into the fabric of everything, waiting to rewrite the stories we tell ourselves about existence. Whether it's order, accident, or something beyond both, one thing's clear: the universe is still speaking. Our job is to listen. The moment science stumbles upon something it can't explain, conspiracy theories rush in to fill the void, and the axis of evil is no exception. From late-night radio shows to viral YouTube deep dives, this cosmic anomaly has been twisted into everything from proof of alien megastructures to evidence we're living in a simulated reality. One popular theory claims the alignment is a cosmic barcode, deliberately imprinted by an advanced civilization as a message to future species. Others insist it's the gravitational fingerprint of a parallel universe colliding with ours, or worse, a sign that the fabric of reality is unraveling. The internet thrives on these narratives, turning complex astrophysics into clickable mysteries that blur the line between speculation and science fiction. What makes the axis of evil such fertile ground for conspiracy? It's the perfect storm of legitimately puzzling science and existential intrigue. Here's a phenomenon even top cosmologists admit they don't fully understand, hiding in plain sight within the universe's oldest light. When experts use phrases like defies physics or preferred direction in space, it's catnip for theorists who see veiled truths behind official jargon. The name itself, borrowed from a political quip by a physicist, only fuels the fire. Label something evil, and suddenly it's a villain in humanity's cosmic origin story, ripe for myth-making. Pop culture amplifies the mystique. The axis of evil has snuck into sci-fi plots, from episodes of Doctor Who to video games like Mass Effect, where it's reimagined as a relic of ancient aliens. Even Hollywood can't resist. The 2022 film Axis, loosely inspired by the Anomaly, depicted it as a celestial countdown to an apocalyptic event. These fictional takes often borrow just enough real science to feel plausible, leaving audiences wondering where fact ends and fantasy begins. The irony: while scientists debate statistical significance, storytellers spin narratives where the anomaly is anything but random, a deliberate clue, a weapon, even a cosmic prison wall. Yet beneath the hype, there's a kernel of genuine fascination. Conspiracy theories often flourish where science is still in motion, and cosmology's biggest discoveries have always started as heresies. Dark matter, once dismissed as a fringe idea, black holes considered mathematical fairy tales until evidence caught up. The axis of evil taps into that same rebellious thrill, the possibility that mainstream science might be missing something monumental. The difference, this time, researchers aren't ignoring the anomaly. They're wrestling with it openly, publishing papers that range from sober skepticism to radical reinventions of physics. The real danger isn't wild theories, it's when they drown out legitimate inquiry. For every thoughtful discussion of the axis of evil's implications, there are a dozen videos claiming it's proof of everything from biblical prophecies to government cover-ups. This noise makes it harder for the public to distinguish between peer-reviewed breakthroughs and pseudoscience. But here's the twist: the conspiracy echo chamber occasionally sparks real scientific curiosity. Some astrophysicists admit they've fielded questions from fans of these theories who later delve into actual cosmology textbooks, hooked by the genuine mystery. At its heart, the axis of evil's pop culture life reveals something profound about how humans cope with the unknown. We'd rather have a wild story than no story at all. Whether it's ancient cultures mapping gods in the stars or modern netizens decoding messages in cosmic radiation, the impulse is the same: to turn chaos into narrative. The anomaly's persistence in our collective imagination isn't just about aliens or simulations, it's a testament to how deeply we crave meaning in the vast, indifferent cosmos. And that, perhaps, is the most human thing of all. Stephen Hawking never directly addressed the axis of evil in his public work, but his revolutionary ideas about the universe's origins might hold clues to this cosmic riddle. Take his no-boundary proposal, developed with James Hartle, which reimagined the Big Bang not as a singular explosion but as a smooth, self-contained event like the rounded tip of a shuttlecock with no sharp edges in space-time. In this model, the universe wouldn't have a true beginning in the classical sense. Instead, time and space would curve back on themselves, eliminating the need for a boundary condition. Now apply that to the axis of evil. If the early universe lacked a conventional starting point, could its structure have inherited subtle asymmetries, like a potter's hands leaving faint ridges in clay? Hawking's framework suggests the cosmos might bear imprints from its own topology, wrinkles that inflation stretched into the large-scale anomalies we see today. Hawking was also fascinated by quantum fluctuations seeding cosmic structure. In his work on primordial gravitational waves, he proposed that microscopic jitters during inflation could have ballooned into the galaxies and voids we observe. But what if those fluctuations weren't perfectly random? If quantum mechanics allowed for correlations across vast distances, a concept echoing his later work on entanglement, the axis of evil's alignments might reflect a hidden quantum preference etched into spacetime. It's a tantalizing thought that the universe's largest structures could trace back to subatomic whispers in its first moments. Then there's Hawking's skepticism about absolute uniformity. He often challenged assumptions, from black hole information lost to the nature of time. When confronted with the cosmological principle's ironclad status, he might have asked, why must isotropy be perfect? The axis of evil could align with his instinct that the universe favors practicality over symmetry. After all, his radiation theory showed black holes aren't the perfect vacuums we once thought. They leak, they fuzz, they defy simplicity. Why wouldn't the broader cosmos, with all its quantum chaos, display similar imperfections? Hawking's later explorations of the multiverse add another layer. If our universe is one bubble in a froth of others, their gravitational tides might have nudged our inflation field off kilter, leaving directional scars. He once mused that colliding universes could leave bruises in the cosmic microwave background, language eerily close to how some describe the axis of evil. While he never tied this explicitly to the anomaly, the connection is hard to ignore. It's as if his theories anticipated such a discovery, waiting for data to catch up to the math. What would Hawking make of the axis of evil today? Given his love for bold revisions, he'd likely dismiss neither the anomaly nor its skeptics outright. Instead, he might trace it back to his lifelong theme, that the universe is stranger and messier than our models allow. Whether a quantum relic, a multiverse tattoo, or just a statistical hiccup, the axis of evil embodies the very unpredictability that made Hawking's work so transformative. And that's the real lesson, not the answers we have, but the questions we're brave enough to ask. Galaxies aren't supposed to line up like soldiers on parade. Yet across the cosmos, astronomers keep finding them doing exactly that, spinning in eerily synchronized formations that defy conventional explanations. Take the work of a team at the University of Leeds who studied over 20,000 galaxies and stumbled upon something bizarre. A significant fraction of these galaxies, particularly in dense clusters, showed their axes of rotation mysteriously aligned with their neighbors, sometimes stretching across hundreds of millions of light years. It's as if an invisible choreographer arranged their spins, a cosmic ballet with steps we can't yet decipher. This discovery isn't isolated. Another study using the Sloan Digital Sky Survey found galaxy pairs separated by mind-boggling distances, up to 6 megaparsecs, spinning in parallel, like synchronized swimmers across an ocean of spacetime. The odds of this happening by pure chance, less than 1 in a million. Even more unsettling, some of these alignments trace back to the same general direction as the axis of evil, as if both phenomena are strands of the same cosmic web, tugging reality into unnatural order. So what's behind this galactic synchronicity? One leading theory points to cosmic filaments, colossal threads of dark matter weaving the universe into a vast, interconnected network. As galaxies form along these filaments, their spins could be shaped by the gravitational currents flowing through them, like leaves aligning in a river's current. But here's the catch. Standard models predict these alignments should fade over time as galaxies jostle and merge. Yet the data shows coherence persisting far longer than expected, hinting at forces we've yet to account for. Others suggest primordial magnetic fields could be the culprit. If the early universe was laced with powerful magnetic fields, they might have imprinted a directional bias on collapsing gas clouds, setting galaxies spinning in tune like cogs in a machine. There's even wilder speculation: quantum entanglement operating at cosmic scales, linking galaxies across vast distances in ways that defy classical physics. It's a fringe idea, but in a universe where the axis of evil exists, can we afford to dismiss anything outright? Then there's the tantalizing possibility that these alignments and the axis of evil are symptoms of the same underlying anomaly, a crack in the cosmological principle itself. If spacetime has a hidden structure, a grain like polished wood, it could nudge galaxies into alignment while simultaneously warping the cosmic microwave background. Picture a potter's wheel spinning clay. As the wheel turns, the clay's shape reflects the motion beneath it. If our universe is similarly spun along a preferred axis, both galaxy rotations and microwave anomalies might be echoes of that deeper asymmetry. Critics push back, of course. They argue that observational biases, like how we measure galaxy orientations or the way telescopes sample the sky, could artificially amplify these patterns. Some simulations suggest that galaxy alignments might arise naturally from the messy dynamics of cosmic evolution, no exotic physics required. But just like the axis of evil, the more data we gather, the harder it becomes to write off these alignments as mere flukes. Whether these phenomena are connected or separate mysteries, one thing's clear: the universe keeps handing us puzzles that challenge our notions of randomness. From spinning galaxies to the axis of evil, the cosmos seems hellbent on reminding us that its rulebook isn't just incomplete, it might be written in a language we're only beginning to translate. And with every odd alignment we uncover, the more we're forced to wonder what other invisible threads are pulling at the fabric of reality. Hidden within the cosmic microwave background's faint whispers lie patterns so subtle, even the most advanced algorithms struggle to spot them until now. Artificial intelligence isn't just assisting astrophysics, it's revolutionizing how we hunt for cosmic anomalies. Machine learning systems trained on petabytes of CMB data have begun detecting irregularities that human eyes would miss, like spotting a single skewed brushstroke in a galaxy-sized painting. One neural network developed at Cambridge recently uncovered a peculiar asymmetry in the Planck satellite's data, a slight but systematic temperature variation that aligns suspiciously close to the axis of evil's plane. The AI didn't just confirm existing suspicions, it revealed finer details within the anomaly, like microscopic fractures in a pane of glass that hint at deeper structural flaws. What makes AI uniquely suited for this cosmic detective work? Traditional statistical methods treat the CMB's fluctuations as noise to be averaged away, but machine learning embraces the chaos. By training on simulated universes, some with preferred directions, some perfectly isotropic, these algorithms learn to recognize the fingerprints of asymmetry with uncanny precision. A team at Princeton fed their AI 10 million synthetic sky maps, varying inflation parameters and quantum fluctuations, until it could distinguish between random patterns and true cosmological anomalies with 97% accuracy. When unleashed on real data, it flagged regions where the temperature fluctuations weren't just unusual, they were statistically impossible under standard models. One such hotspot, a stretch of sky where the axis of evil's alignments appear to intersect with a previously unnoticed cold spot, as if the universe's fabric had been stretched taut between two invisible anchors. The real power of AI lies in its ability to think beyond human biases. We're taught the universe should be isotropic, so our analysis methods often assume it. But machine learning has no preconceptions. When researchers at MIT trained an unsupervised AI to categorize CMB patterns without guidance, it grouped the data in ways that defied conventional cosmology, including identifying what it labeled Cluster 7. A mysterious alignment of hotspots spanning 15 degrees of sky, positioned at a precise 60-degree angle to the axis of evil. Was this coincidence or evidence of a larger geometric structure woven into space-time? The AI couldn't say, but its discovery sent theorists scrambling to their chalkboards. Some of the most exciting developments come from adversarial networks, where two AIs compete, one generating synthetic CMB maps, the other trying to spot fakes. Like art forgers and detectives locked in an endless duel, these systems push each other toward ever greater refinement. The result: algorithms so sensitive they can detect inflation-era gravitational waves 100 times fainter than current methods allow. A joint Caltech-Google project recently used this technique to uncover ripples in the CMB's polarization patterns that curve unnaturally along the axis of evil's orientation. If confirmed, these could be scars from cosmic strings, space-time defects predicted by string theory, or something even stranger. Yet for all their prowess, AIs bring new challenges. Their decisions often resemble black boxes, offering answers without showing their work. When one deep learning model insisted it had found a perfect spiral pattern in the CMB, astronomers spent months debating whether it had uncovered new physics or simply hallucinated statistical artifacts. The solution: hybrid approaches that marry AI's pattern recognition with physicists' intuition. At the University of Chicago, researchers are developing explainable AI systems that justify their findings using the language of quantum field theory, transforming inscrutable neural network weights into equations a human can interrogate. The next frontier: real-time anomaly detection from next-generation telescopes. Imagine an AI monitoring the CMB-S4 experiment's data stream, flagging irregularities before they even reach human analysts. Such systems could spot transient phenomena, brief warps in the microwave background that might reveal colliding bubble universes or decaying dark matter particles. There's even talk of using quantum machine learning to analyze the CMB's quantum origins directly, creating feedback loops where quantum computers study quantum fluctuations that birth the cosmos. Whether AI ultimately solves the axis of evil or simply reveals how much deeper the mystery goes, one thing's certain: our cosmic cartography is entering uncharted territory. These algorithms aren't just tools, they're collaborators, pushing us to see the universe not as we expect it to be, but as it truly is. And in that tension between human intuition and machine revelation, we might just find the keys to reality's best-kept secrets. Science thrives on disagreement, and few topics ignite as much debate as the axis of evil. Within academic circles, reactions span the spectrum from those who dismiss it as statistical noise to researchers willing to bet their reputations on its revolutionary implications. The divide often falls along generational lines. Established cosmologists whose careers were built on the bedrock of the cosmological principle tend to wave it away as a measurement quirk. One Nobel laureate famously compared it to seeing the Virgin Mary in a piece of toast, a trick of pattern recognition, not divine intervention. Meanwhile, a younger generation of physicists, raised on anomalies like dark energy and quantum entanglement, are more willing to entertain radical explanations. On conference stages and preprint servers, the arguments grow heated, sometimes uncomfortably so. At a 2018 Cosmology summit in Lisbon, a heated exchange between a Princeton professor and a postdoctoral researcher over the anomaly's significance nearly derailed the entire panel. What makes this debate so volatile is what's at stake. For skeptics, accepting the axis of evil as real would mean discarding a foundational assumption of modern cosmology, that the universe has no preferred direction. It's not just about one anomaly, it's about whether our entire framework for understanding the cosmos is flawed. As one critic put it, you don't demolish a skyscraper because one window is cracked. But supporters counter that science progresses precisely by confronting such cracks. They point to history. When the orbit of Mercury didn't align with Newton's predictions, physicists didn't dismiss it, they discovered general relativity. The axis of evil, they argue, could be our generation's Mercury moment. The statistical battleground is equally contentious. Teams have spent years developing ever more sophisticated algorithms to test whether the alignments could emerge randomly. One camp publishes papers with titles like "The Axis of Evil, a Persistent Illusion," demonstrating how certain data processing choices can artificially enhance symmetries. Another group fires back with analyzers showing the anomaly survives even the most aggressive noise removal techniques. The dueling studies have become so technical that some journals now require authors to include translation, paragraphs explaining their math in plain language, a tacit admission that even peer reviewers struggle to pass the escalating complexity. Beyond academia, the controversy spills into public discourse. Science communicators grapple with how to present the anomaly without sensationalism or undue skepticism. Podcast hosts debate whether calling it the axis of evil was a brilliant marketing stroke or a disservice to sober science. Meanwhile, amateur astronomer forums buzz with DIY attempts to analyze public CMB datasets, sometimes uncovering oddities professional teams missed. This democratization of cosmic detective work has its pitfalls, like the viral but debunked Axis conspiracy video claiming scientists were hiding the truth, but it also reflects something beautiful, a public genuinely wrestling with profound questions about reality's fabric. At its core, the debate isn't really about data, it's about how science confronts the unknown. Do we protect our hard-won theories at all costs, or do we follow anomalies wherever they lead, even into the abyss of rewritten textbooks? The axis of evil forces that choice upon us, making it one of the most consequential puzzles in modern cosmology. And until the next generation of telescopes delivers verdicts, the arguments will rage on, not as weakness but as science working exactly as it should. If the axis of evil isn't just a cosmic illusion, if it's real, then physics stands on the brink of its next great upheaval. Picture the moment before relativity shattered Newton's clockwork universe, or quantum mechanics rewrote the rules of reality. The implications could be that profound. At its core, this anomaly challenges the cosmological principle, the idea that the universe is uniform in all directions. If that foundational assumption cracks, everything built upon it, from the Big Bang model to dark energy's behavior, might need re-evaluation. We could be staring at the first thread of a cosmic tapestry woven with entirely new physics. One tantalizing possibility is that resolving the anomaly might force us to rethink gravity itself. Einstein's general relativity has reigned supreme for over a century, but what if it's incomplete? Modified gravity theories like MUND already suggest tweaks to Newton's laws at galactic scales. If the axis of evil reveals a preferred direction in space-time, it could hint at gravity operating differently along certain cosmic axes, a directional dependence never before considered. Imagine gravity as a river flowing stronger in one direction than another. Such a discovery wouldn't just tweak equations, it'd rewrite them, potentially unifying gravity with quantum mechanics in ways we've only dreamed of. Then there's dark energy, the mysterious force accelerating the universe's expansion. Current models assume it's uniformly distributed, but what if it's not? The axis of evil's alignments could suggest dark energy flows in cosmic currents, pooling in some regions and thinning in others. This wouldn't just explain the anomaly, it'd transform dark energy from a static placeholder into a dynamic, evolving force. Future telescopes like ESA's Euclid might map these flows, revealing whether the universe's expansion is as uneven as its microwave background, but the most radical outcome. Evidence of a multiverse. If the anomaly stems from a collision with another bubble universe or a gravitational tug from beyond our cosmic horizon, it'd be the first empirical hint that we're not alone in the metacosmos. String theorists have long predicted such interactions, but without data, the multiverse remained pure speculation. The axis of evil could change that, offering a fingerprint of realities beyond our own. Suddenly, the philosophical fantasy of parallel universes would become a testable scientific hypothesis. Of course, not every mystery leads to revolution. The axis of evil might still fade into obscurity, a statistical quirk amplified by our pattern-seeking brains. Yet even its persistence as a puzzle teaches us something vital, that the universe refuses to be boxed by our assumptions. Whether it's a flaw in our models or a flaw in reality, the anomaly reminds us that physics is a living, breathing science, one where the next great discovery might be hiding in the data we've already collected, waiting for the right mind to connect the dots. The stakes couldn't be higher. If the axis of evil holds, we're not just correcting a textbook, we're rewriting it from scratch. And that's the exhilarating promise of cosmology. Every anomaly, every contradiction, is a doorway to a deeper understanding. Whether it swings open or slams shut, the journey to find out will redefine our place in the cosmos. So where does this leave us, staring into the cosmic abyss, confronted by an anomaly that refuses to fit neatly into our models? The axis of evil isn't just a scientific puzzle, it's a humbling reminder of how much we still don't know. Whether it's a flaw in our measurements, a ghostly handshake from a parallel universe, or evidence that gravity itself plays by different rules in the cosmic dark, one thing's certain: the universe is far stranger, far more mischievous than we ever imagined. Think about what's at stake here. For centuries, we've built our understanding of reality on the idea that the cosmos is uniform, unbiased, no special places, no preferred directions. But if the axis of evil is real, that foundational principle crumbles. Suddenly, the universe might have a grain, a tilt, a hidden spine running through its fabric. It's like discovering the ocean has a current flowing in one relentless direction, invisible from the shore but shaping everything beneath the surface. That's the scale of this revelation, not just a new fact to jot down, but a paradigm shift waiting to happen. And yet, for all its disruptive potential, the axis of evil is also an invitation. Every great leap in science began with an anomaly, a detail that didn't fit, a number that refused to add up. Einstein's relativity emerged from the wobble of Mercury's orbit. Quantum mechanics was born from the ultraviolet catastrophe's glaring contradiction. Today, we're standing at the edge of another such cliff, peering into the unknown. The difference, this time, we've got tools Einstein couldn't dream of. AI parsing cosmic data, telescopes mapping the sky in unprecedented detail, and a global community of curious minds dissecting every clue. Here's the beautiful part: the next breakthrough might not come from a lab or a satellite. It could start with you staring at a star chart on your laptop or sketching equations on a coffee-stained napkin. History's full of amateurs who cracked cosmic mysteries, from Heinrich Olbers wondering why the night sky is dark to the schoolteacher who discovered pulsars in radio static. The universe doesn't care about credentials. It reveals its secrets to those who look closely, question boldly, and refuse to accept "we don't know" as a final answer. So keep your eyes on the sky and your mind open. The axis of evil won't be the last cosmic curveball. Somewhere out there, another anomaly is lurking, waiting to rewrite the rules. Maybe it's hidden in the flicker of a distant quasar, or encoded in the spin of a galaxy cluster. Or maybe, just maybe, it's tucked into data we've already collected, overlooked until the right pair of eyes connects the dots. The cosmos is a story still being written, and the next chapter could belong to anyone daring enough to turn the page. After all, the greatest discoveries aren't just about finding answers, they're about learning how to ask better questions. And in a universe this wild, the questions are just getting started.